As you get ready for this exercise, it's important to have two tools or pieces of information with you. One is the tutorial. The tutorial that contains all the questions for the exercise and all the instructions, all the information that you're going to need to answer the questions. And a copy of the answer sheet, which in this case is a worksheet where you're going to list your assessment of the different volcanic hazards that we're going to be addressing and how they impact the different towns and communities in this fictitious location. Okay, so having those two things ready will help you move along with the exercise. Okay, so for this module topics, we are covering magma, the formation of magma, the difference between magma and lava, and looking at the expression of magma reaching the surface, which is a volcano. The physical expression of magma reaching the surface is a volcano. So we're going to look at different types of volcanoes and volcanic features, and look at eruptions and hazards from those eruptions. Okay, so those are the 5 key concepts for the module, but this exercise focusing particularly on the last two topics. Those are the ones that we're going to be focusing on this exercise. Okay, so a little bit of a background first, so we can understand what are the different types of eruptions and how they will produce different volcanic products, and how will those products impact communities. So when we look at hazards, so it's important to understand where and how those products are formed, so we can understand what type of impacts they will have. So there are 2 very different types of volcanic eruptions, and you might have seen that some volcanoes are very explosive, and that's the example on the right. So the example on the right, you see those types of volcanoes that when they erupt, the whole mountain is blown apart, lots of ash is thrown into the sky, miles into the sky, cause ashfall and displacement of communities all around them. So it's a very destructive and disruptive type of eruption. On the other end, we have what we call effusive eruptions. And in those, the lava just bubbles up to the surface and it flows like a river, very fluid lava. Those are not, they are called benign eruptions because they do not cause loss of life. The lava, even though the lava moves large distance from the volcano, but they're always moving at a slow pace. You could escape that lava just by a brisk walk, or it would be enough to escape that. So, but it can cause some property damage and destruction as the lava moves away from the volcano. It can destroy forests, villages, buildings, roads, and other infrastructure. So although it can be very damaging, it's usually not, it doesn't usually it's not associated with loss of life, like the explosive eruptions are. And the impact is a little more limited as well to the reaches of the lava. Okay, so for example, the lava is not going to go uphill. So places that are uphill are not going to be affected by the moving lava. But if you have an explosive eruption, it doesn't matter if you are in a hill or not, that hot ash might be falling for miles away from the volcano. And that disruption can cause a lot of damage. So two very different types of eruptions. So what is at the heart of this difference? So why are they so different? And the reason is the composition of the magma, what the magma is made of. So magmas that are rich in silica, produce explosive eruptions. But magmas that are poor in silica produces effusive eruptions. And of course, a magma that is rich in silica is poor in something else, and that something else is magnesium and iron. And of course, magmas that are poor in silica, they would be rich in magnesium and iron. So those two work in opposite directions. Magmas that are rich in magnesium and iron are poor in silica, and magmas that are rich in silica are poor in magnesium. That's why we give them those two extreme names. Mafic, or as they're rich in magnesium, that's the Ma stands for, and ferric. So mafic, magnesium, and ferric, which is the Latin name for iron. That's why the symbol for iron is Fe. Mafic means rich in magnesium and iron, and as a consequence, poor in silica. On the other of that, we have felsic. Felsic magmas rich in feldspar, silica. Feldspar and silica. Okay, so those are felsic magmas. So felsic in one extreme, rich in silica, poor in magnesium and iron, and mafic on the other extreme, rich in magnesium and iron, poor in silica. So the composition of the magma is a very important factor determining the type of eruption that we're going to have. Okay, so here's a summary of all magmas do have silica, but mafic and ultramafic magmas, they have very low amounts of silica compared to the felsic, silica-rich magmas. Okay, so silica is the mineral that makes the eruption very explosive or not. Okay, so now let's do a quick look at the types of features and the types of volcanoes that result from those very different magmas. So we can identify two types of volcanoes. So one is the classic conic volcano. You can see here is this very steep sides, sometimes with smoke coming out of it, volcanoes. So those are called composite volcanoes. And they are called composite because they are formed by a composition of layers, ash and lava. And each of those layers represents a different eruption. So when there is an eruption, a layer of ash and lava deposits on that. And because the lava is very viscous, it doesn't travel very far from the volcano, it creates a layer on the flanks of the volcano of lava. And then there is ash associated with that because those explosive eruptions have lots of ash, and that ash falls on top of that layer of lava. Okay, so you have successive layers of lava and ash or pyroclastic material. Okay, so that's a composite. Okay, that's the classic view. When you think of a volcano, that's what you think of. And then on the extreme, with very fluid lavas, in which ash is rarely produced, if produced at all, we have the shield volcano. A shield volcano. And it's called a shield volcano because when you look it on the side, as you can see in this picture here, it looks like a shield. It looks like a shield. Okay, so shield volcanoes do not have that conic structure that we see in a composite volcano. Okay, so we don't see that in a shield volcano. Instead, they have gentle volcano with not so steep sides, as you can see here in this drawing, not so steep sides. So that's Mauna Kea in Hawaii. Okay, very gentle, and that's because the lava can move long distances from the vent, from the crater, and that creates that very smooth and flanks in the volcano. Okay? So shield volcano on one side, composite volcano on the other. Now you might think, okay, so when we compare those two, which one would be bigger and taller? Bigger in size, taller from the bottom up. Bigger in extension, taller in size. So is it Mount Fuji, a classic example of a composite volcano? Or is it Mauna Kea, classic example of a shield volcano? And you might be tempted to say that Mount Fuji is the one, but you would be wrong, because in fact, the size of Mount Fuji doesn't compare with the size of Mauna Kea. You can see here in this picture. So Mount Fuji is about 3,700 meters in tall, with about 6 kilometers inside from base to base. Okay? And so those do not compare with the sizes of Mauna Kea. Mauna Kea is 200 kilometers in width, which is much larger than Mount Fuji, and also in the height above sea level, so almost 3 times as tall as Mount Fuji. And that's only if you consider sea level. If you consider just sea level, Mauna Kea is about 3 times bigger than Mount Fuji. But in fact, because Hawaii is an island, Mauna Kea was growing from the bottom of the ocean, which is thousands of miles and thousands of meters below sea level. So in fact, if you add all this size from the bottom of the ocean up to the sea level, you add another 15, almost 15,000 meters to the size of Mauna Kea, which makes it the largest mountain on the planet, largest than tallest than Mount Everest. Okay, so shield volcanoes, although they seem very unassuming, they are in fact very large in all types of measures. Okay, so let's look then at the hazards associated with eruptions from those volcanoes. So as you can imagine, because those volcanoes are so different, they will produce different types of hazards. Okay? So you can think that in an explosive eruption, ash fall is a big hazard. The hot ash falling is a significant hazard. That type of hazard doesn't exist in an effusive eruption. There is very little, if any, ash being released. Okay, but if you think of lava flow damage, then damage from lava flow is going to be more prominent in effusive eruptions than in explosive eruption, because the lava is not going to travel too far. It's too viscous, too thick to go too far from the volcano. It cools quicker as well, so it hardens quicker. So lava flows are not a big issue for explosive eruptions, but can be a big issue for feasible. So different types of hazards are associated with different types of eruptions. So here's a summary of those major hazards. So we have, as we mentioned, ashfall, okay, also known as tephra. Then we have mud flows. If there is rain or snow that melts when the eruption happens, that mixes with the ash and the pyroclastic flow, and it rushes down the hill, causing great damage to property and even nature, trees and pastures and croplands. They can be greatly damaged by those fast moving flows of mud and rocks and debris. Okay. Then we have what's called a debris flow, which is not as fluid as a mud flow, but it also brings some material with them, carries a lot of material with them. It could be trees, it could be rocks, but it doesn't move as fast as a mud flow. Okay, but it behaves very much like a mud flow. Then we have the pyroclastic flows, which includes a smaller material like ash as well, but heavier than the ash in the ash cloud. So the ash in the ash cloud is lighter, it's smaller, like dust debris. So they stay up high, but the pyroclastic material is larger in size, so it moves along the flank of the volcano. Then we have lava flows, which prominent in fluid volcanoes, and volcanic gases that are associated with the eruptions. Okay, so those are the 5 major groups, because we put debris flow and pyroclastic flows together. There are variations of the amount of fluid, the size of the material that constitute each of those types. So those are the 5 types of hazard that we're going to be evaluating in this exercise today. So ashfall, mud flows, pyroclastic flows, lava flows, and volcanic gases. And what we're going to be doing is evaluating the risk of loss of life or loss of property from each of those hazards. And we're going to classify them as high risk, moderate risk, or low risk. Okay. And where are we going to apply those evaluations? We have here a fictitious location, a county map that has a major city, that's Hazard City right over here, and a few smaller communities around, towns in the county. Those are Blaney over here, Crossroads, Hopper, Hutton, and Wrightstown. So those are smaller communities, 5 smaller communities in the county, and the largest city is Hazard City. This county, another big feature of this county is that it has a volcano, a mountain that is in fact an active volcano called Lava Mountain. And so what has happened recently is that people that live in this area have been alarmed by recent developments related to the volcano. They start seeing a smoke coming out of the tip of the volcano that seemed dormant for many years, but suddenly is having that smoke coming out of the volcano. There is a smell of sulfur in the air. There are earthquakes and ground tremors that happen from time to time. They find animals that are dead on the fields by asphyxia. So all of those are signs that an eruption might be imminent. An eruption might happen. So those people are concerned. So they hired us, the experts, to do an assessment of the risk that each of those communities will be facing if an eruption takes place. If an eruption takes place, okay? So we're going to evaluate the risk of loss of life or property for each of those communities, and also for neighborhoods within Hazard City, which is the largest city in the county. So if you blow up, so here in your answer sheet or your assessment sheet, you have the towns over here in the top of the sheet. So Wrightstown, Hutton, Crossroads, Hopper, and Blaney, those 5 communities. And at the bottom of the answer sheet, you have the neighborhoods within Hazard City. So if you look here, Hazard City is this little town over here. If you blow that square up, that's what you see over here. So this is a city map, and it has different neighborhoods: Riverside, Ralston, Point Park. Those 3 are in the floodplain. Here you see the Clearwater River that runs through the city, and it has those 3 communities. Those are houses that are smaller, not so expensive. Some of them are trailer parks, like here in Point Park and in Riverside. So those are not very well constructed homes. They're prone to flooding because they are in the floodplain here as well. But we also have communities that are here up, about 40 feet above the floodplain, and those are Hickory Estates, a kind of semi-commercial and residential community. The downtown area, which is mostly commercial real estate. We have here Shopping Mall, which is a suburban district with residents and a large shopping mall, and a primarily residential area up in the hills of Walnut Heights with single-family homes, multi-story homes, newer construction. Okay, so different communities, 7 communities within Hazard City, and we're gonna evaluate the risk here on the bottom section of your assessment sheet. Okay, so at the top, the towns in the county, and at the bottom, the neighborhoods in Hazard City. Okay, so again, as I mentioned before, we're going to evaluate the risk of loss of life or property from each of those volcanic hazards listed here at the top for each of those communities and neighborhoods. And we're going to evaluate the risk to be high, moderate, or low. Now, the next question is, how am I going to do this? What kind of information do I need to make that assessment? So for each of those hazards, we're going to be evaluating 3 pieces of information. 3 pieces of information. Okay, so for ashfall, for example, what do you think are the 3 pieces of information that I need to be able to make that assessment if the risk of loss of life or property is high, moderate, or low? What are the 3 pieces of information that I need? So you might imagine that one of those is because the wind is going to depend on the wind is blowing, and it seems like in this case the wind is blowing that way. So the wind direction is going to be an important factor. Okay? So the wind, you also going to need to know, okay, when there is an eruption, usually what is the extent, distance that the ash can travel downwind? What is the average range of area affected by the ash fall? Okay, so you need to know that. So the distance that the ash can travel from the volcano. Okay, and the last one, which might not be too obvious as the first 2, is soil deposits in around the area that you're assessing, because those soil deposits will tell us if an eruption in the past, when the volcano erupted in the past, and it has erupted many times in the past, in a past eruption, how far did the ash go? Okay, so if in the past the ash has gone a certain distance, it is reasonable to expect that in a future eruption, the ash is going to travel at least the same distance. Okay, so we look for deposits from past eruptions. Okay, so those are the three criteria that three pieces of information that we're going to be evaluating. So the wind direction, the distance that ash travels, and the deposits from past eruptions. So where do we going to get that information? So that information is provided in your tutorial, in different pages of your tutorial. So for example, for the wind direction, you're going to find that information on page 3. So I want you to read page 3 and find what is the direction that the wind blows predominantly. Okay. For the distance of travel, we're going to look for on page 5. Okay. So on page 5, you're going to read a little bit of information about ashfall. What happens when you have ashfalls? How far does ash can travel from the volcano? What's the area that is affected by that? Okay, so you're going to read that on page 5. The last piece of information are the deposits from past eruptions, which you're going to find on pages 13 to 16. Okay, so basically what you have there is a core that was dug through the ground, and when dug back, it shows the different layers of sediments accumulated in that particular location. So the top of the core is the most recent deposit, and the bottom is the oldest deposit. So, for example, in this location number 7, and the locations are all in the map. So if you go back to the map, we're going to see that there are numbers. You see those numbers in red all across the map. Okay. You see number 1, 2, 3, 4, 5, 6, 7, 8, 9, and in Hazard City as well. If you look at Hazard City, you see a couple of numbers there. You see number 11 is here in floodplain, and number 10 is up here in the higher elevation. So in each of those locations, a core was drilled into the ground and produce those different deposits. So for example, number 7 here, you see that there is stream sediments there. So it's probably close to a stream. So there is active erosion by that stream taking place. But you also find some mud, layers of mud over here, indicating that mud flows, especially if you have boulders and plant debris, that's an indication that there was a mud flow from a previous eruption that brought material to that location from that mud flow. Okay, number 8 here, location 8. So here's the surface today, and here's a deep deposit. So that core has drilled into the bedrock. So it's a very thin layer of sediment up top, and that sediment includes mostly soil, which is formed from the weathering of that bedrock. But there is also, and most intriguingly, there is a layer of over here in this location number 8. That's the one that is important to us. So if ash came to that location 8 in the past, and that was the ash accumulating that previous eruption, then it's very much certain, you can be very much certain that the ash is going to travel at least that far, if not farther than that location. Okay, you see similar thing online, although it's a thinner layer, meaning that it was a little farther away from location 8, so we receive a lot less ash than location 8. But again, because there is a layer of ash there in location 9, in the past, from a past eruption, it is very likely that in a future eruption, the ash is going to travel at least that far. Okay, so we use the deposits to get information from the past that will inform what's going to happen in the future. So the past is the key to the future. Okay, so what I want you to do right now, pause the video, go to page 3, and find wind direction information. Find the information for the wind direction on page 3. So pause the video right now and find that information so you know what is the direction of the wind. Okay. Then once you're done, move to page 5, read that page, and find the distance that ash travels after an eruption. How far can the ash travel? And if you find the distance in kilometers, you can just transform it to meters 1-to-1, even though it's not the same thing. 1 kilometer is about 1.7, 1 mile is about 1.7 kilometers. But you can, for the purpose of this exercise, you can just assume that it is 1-to-1 because the map, the scale in the map is in miles. The scale in the map is in miles. And because the scale in the map is in miles, you can transform any talk about kilometers in the readings 2 miles, just to avoid having to do conversions here. Okay, so pause the video now, go to page 5 and find the distance that ash travels, the distance that ash travels. Okay. So now that you have the 3 pieces of information, you know the direction that the wind is blowing, you know how far, if there is an eruption right here, how far will the ash travel in all directions? How far from the volcano it travel? So by knowing this, for example, if that's as far as the ash is going to travel, then Crossroads is not going to be affected. Hazard City is not going to be affected. Blaine is not going to be affected. But Hopper, Hutton, and probably Wrightstown will be affected. So knowing the distance will help you assess which communities will be affected. Okay, so now that you have that information, you can start making your assessment. Okay, so you're going to look, for example, for Wrightstown. So you can start with Wrightstown over here. So you're going to see, in terms of the wind, is Wrightstown. So here is the volcano, and so here is the downwind area, and here is the upwind area. So places that are downwind, like Hutton and Wrightstown, they likely get an assessment of high if you are just considering the wind. If you just consider the wind, assessment for Wrightstown and Hutton will be high, but the assessment for Crossroads, Hazard City, Blaney, and Hopper would be low, okay, because they are upwind. So the wind's going to blow the ash to the west. So here's north, south, east, west. Okay, so just the wind, we have the assessment for the different communities as high or low. Okay, so then we're gonna look at the order. Let's look at the distance. How far does the ash can travel? So you got that information from page 5. And you know that ash can travel hundreds to thousands of kilometers from the volcano. So pretty much everywhere in that map is going to be within that range. Okay, so it's going to be high in terms of distance. It's going to be high for everybody. So all the communities we get a assessment of high because they all are within the range of the volcano. So for those communities that already have high for wind, for distance, you already have 2 out of 3, so the assessment for those is going to be high. Because even if the third one is low, based on deposits, but you already have 2 that are high, 2 pieces of information says high risk, 1 piece of information has low risk, the assessment will be high. So that's why you're evaluating 3 pieces, because that will allow you to make an assessment. Okay, but for the other communities, downwind from the volcano, you have 1 low, high, 1 low and 1 high. One low and 1 high. So you need that third piece of information to make final judgment. Okay. So then you're going to look at deposits, for example, for those that are here. Let's say Crossroads. Crossroads is right over here. It's low for the wind because it's upwind, so low for the wind, and high for the distance because it is within the range that ash travels. Then when you look at the deposits, the closest one is going to be at number 8 over here. So you're going to check if was there ash past eruption that reached this location. So you go to page 13 to 16, and you're going to find that, yes, there was a layer of ash in that location. So that means that ash came that far. So here's the volcano, and ash came that far. Okay, so if ash came that far, is it a stretch to say that ash is going to go that far? Not really. Okay, so there is a very good chance that ash is going to travel that far as well, if it did travel that far. It's not that much of a distance. It might be, what, 2 miles, 3 at the most, beyond what the distance that it traveled here to point 8. So based on the, ideally, we would have, if we were in the field assessing that, we would have a deposit collection closer to Crossroads. But in this case, we do not have it. So we have to play with what we got. And so for that, it would be an assessment of high as well, because ash is very likely to come that far as well. So 2 highs, 1 low, the assessment for Crossroads would be high as well. So that's how we're going to go about doing it for each of the communities. And then you're going to look at the neighborhoods within the city and do the same type of assessment. Okay? Now, so far we had high and low assessments. When do we use the moderate? So the moderate is only you're gonna use the moderate when the situation where one piece of information says low or high, and the other says the opposite. So in this case, low for wind, high for distance, and the third one is inconclusive. If the third option is inconclusive, then you are left with 1 low, 1 high, no definition there. In that case, you go for the moderate option, the moderate assessment, okay? But for most of those, you're gonna either end up with high or low. There will be very few situations in which you're gonna get the moderate assessment there, okay? So what I want you to do right now is to pause the video, work on the assessment for ashfall for all of those communities. So go community by community and make your assessment. High, moderate, or low. High, moderate, or low. Okay, so that's what you're going to be doing for all of that. So pause the video right now and work on this one for ashfall. Evaluate ashfall for each of those communities and neighborhoods within Housing City. And when you're done, come back for us to discuss question 2. Okay, now we're going to do this same game, but now assessing the mud flow. So again, we need 3 pieces of information to make that assessment. And what would be the 3 pieces of information? So remember, we had for ashfall, we had wind, distance, and deposits. That was for ashfall. Now, for mud, wind is not going to play a role because wind is not going to affect where the mud is going to go. Distance, yes, because the lahars will move, the mud flows, they will move a certain distance from the volcano on average. And that information is available to you on pages 7 to 8. So on page 7 to 8, you're going to find how far the mud flows will travel from the volcano. So read that. You can pause right now to find that information on how far does the mud travel from the volcano. So the other piece of information, so distance is okay. You're also going to use deposits. You already know how to use it to find the deposits. So just look at those numbers, look at the layers. But instead you're looking for ash, now you're looking for mud. Mud and debris. Okay, so if you find those, is an indication that a mud flow has come to the location in the past. Now we need a third piece of information. And what's going to replace the wind here is going to be the elevation of the terrain, the relief of the terrain. Because the mud is going to always move downhill. It's not going to go uphill. So knowing where are the locations that are uphill and the locations that are downhill in your map will help you establish where will the mud move to. So that's called elevation. Okay, so the elevation is the third piece of information. So here it is, elevation, the relief of the terrain, the distance that mud travels, and the deposits from past eruptions. Okay, so how do you determine the elevation of the terrain? Which areas are high, which areas are low? It's very simple, in fact. You just look at the water. Where is the water flowing in your map? Okay, the water is always going to be flowing from high elevations to low elevations. So you see here the Clearwater River flowing here from west to east. So it's flowing in that direction. Okay, how do I know that? I know that because of this tributary here, the Palouse River is flowing towards the Clearwater River. And how do I know that again? Because you look at the path of each of those little streams flowing from the mountain. They are moving towards that direction. So we can, if we divide the map into quadrants, so let me do this a little different, use a different color. If I divide the map into quadrants, so here is the northwest, northeast, southwest, and southeast. And if you can see that the southeast quadrant is the lowest elevation because all the water is flowing towards that quadrant. The northeast is relatively high. Northwest definitely high. You see how all the water is moving away from the northwest. They're also moving away from the southwest. So northwest, southwest, and northeast are fairly high elevation compared to this valley that we see over here. So there is a valley that flows in that direction, low elevation there. So now you know what the elevation is. You'll be able to use that as one assessment piece. Yeah. For the distance of travel, again, you're going to look at page 7 and 8 and find out how far does the mud travels when there is an eruption, okay? And you already know the deposits from past eruptions. Those are in page 13 to 16. So you're going to use those 3 pieces of information to evaluate, to assess the risk for each of those communities, the 5 communities, and the neighborhoods within Hazard City. So pause the video right now, and you're gonna do that assessment, okay? So pause the video, and you're gonna make your assessment for the mud flows here for each of the communities, high, moderate, or low, okay? So now for the next 2, the pyroclastic flows and the lava flows, the clues or the 3 pieces of information that you're going to use is going to be exactly the same that you use for mud flows, because both the pyroclastic flows, as you can see here, and mud flows, the pyroclastic flows, and the lava flows, they all flow downhill, okay, downstream. So you're going to be using the same 3 pieces of information, which are the elevation, the distance that it travels, although the distance is going to be different for pyroclastic flow, different from lahars, and different from lava flow. So you have to look at each specific page to find the distance, and deposits will be the same, okay? So of course, for pyroclastic flows, you're going to be looking for a mix of ash and boulders, and all the other pyroclastic material. Okay? And for lava flow, you're going to be looking for lava in your deposits. Okay? So for the distance of travel or plastic flow, you're going to be looking on page 12. The distance that lava flows travel, you're going to be looking from pages 9 and 10, where I discuss this lava flow. And there will be enough for you to make that assessment. So you're going to be using those 3 criteria, the elevation, distance, and the deposits to assess that for both the communities in the county and the neighborhoods in Hazard City. And you're going to make your assessment here for pyroclastic flows, here for lava flows, okay? So pause the video right now and work on those 2 questions, 3 and 4, the assessment of pyroclastic flow and lava flow. Okay, for the last question on this assessment, we're going to now look at gases, volcanic gases. So we're going to assess the risk that volcanic gases gases do not cause loss of property, but they might kill livestock, household animals, or even people if they are exposed to these noxious gases. Now, for the gas, it's going to be different than everything else, because for the gas, we only had 2 pieces of information. So the likelihood that you're going to get a moderate assessment here is going to be high, because you're only going to have 2 pieces of information. If the 2 are low, then the assessment is going to be low. If the 2 are high, the assessment is going to be high. If one is high, the other is low, you're going to have a moderate assessment. And what you're going to be looking for, so things that affect gas is going to be the wind, because gas is highly dependent on the wind direction, even more than ash. Okay. And also you're going to look for how far gas can travel from the volcano. Okay, so again, you're going to find that information. So the wind you already know, you get that on page 3. And for the distance that gas travel, you're going to look at page 11 to find out usually how far from the volcano does it travel. Okay, then you're going to use those 2 pieces of information to make your assessment for each of the communities and neighborhoods within the area. Okay, and you're going to list your assessment, high, moderate, or low, into those boxes over here. Okay, so pause the video now to work on this last question. And that will conclude our exercise for today. If you have any questions, just get in touch with me. Thank you.